Today's lab is lab number 8, which is about understanding a physical model for steady state seepage. So there are two objectives. The first is to just develop an appreciation for using physical models to understand geotechnical or geoenvironmental systems. Just the way doing a lab, that hands-on experience is helpful in understanding concepts we learn in classes. An actual model of a system is also very helpful. So if we are going to construct a dam and going to understand how the water flows through it, by creating a model, we can understand it in a laboratory setting under controlled conditions. So physical models can be important or are important in geotechnical and geoenvironmental engineering. The second purpose is that there are physical models that we can construct. Then there are analytical methods that uses physics, mathematics, and other sciences. Right? An example would be this Laplace equation for steady state seepage under a hydraulic structure. So this equation was developed based on physical processes or physics and mathematics. So in order to do that, we make certain assumptions, right? We make assumptions such as Darcy's law is valid. We make assumptions such as the soil is incompressible, water is incompressible, and so on. So we want to verify that whatever we are going to get as results from these analytical methods, they actually are reliable. And that's why field testing or physical models can be very useful. But field testing can be very expensive. So physical models often are much cheaper to do. So in this particular lab, we are going to use a physical model to verify analytical methods. And in this particular case for Laplace equation, we have two analytical methods. One is graphical and the other is numerical, where we are going to use program Seepage. So for this physical model, we are going to start with a plexiglass transparent container that we see here in the upper photograph. So it has a hydraulic structure already built into it. So this container is about 6-7 centimeters wide in the direction perpendicular to the picture. And within that, we have glued into this structure. So the structure we are seeing here is the hydraulic structure. Okay, so we are going to study this two-dimensional problem by creating a model and see if there was soil around this structure, how the water will flow. So what we are going to do is fill it up this container with sand. Okay, so and then we are going to create, this is an inlet, so we are going to connect this to a water reservoir and create an upstream reservoir, and this water is going to flow from upstream reservoir to downstream, and we have this outlet here, and we are going to create a downstream water surface. So under this total head difference between the upstream and downstream water levels. The water is going to flow, and if we keep the heads upstream and downstream constant, then the water is going to flow under steady conditions, and that's why it's called steady state seepage. And then we have, then we are going to measure the water that comes out of the outlet under the steady state seepage condition, volume Q over some time t, which gives us the flow rate. And then we also have three piezometers here. This is P3, this is P2, and this is P1. So these have these tubes sticking out, and if we measure the water levels in those, that gives us the pressure heads or piezometric heads at that locations. So in order to make the visualization better, we have put a piece of paper in front of the container so we see the dam easily. And then we start by putting a tube here at the bottom, and that tube comes out, and then we send some water through it after we create our soil layer. And then by sending this water, the soil is going to saturate from bottom to top. And then we are going to put some dye here, and then when we create head difference, this dye is going to spread through the soil, and those are going to be like our flow lines. So here is our sand model. If you see, we have three dyes that we have put, and you will see how we inserted them into the soil in the video that we have provided. And then right now in the photograph, the water level upstream is not quite high. It's right now only here, but eventually we are going to fill it up all the way to the inlet level. So there is a water reservoir here. And then we are maintaining some downstream water level here to the level of outlet. Now you will see these sponges here on both upstream and downstream on top of the soil surface, and that's done just to protect the soil surface so it doesn't erode when the water is poured onto it, if we ever need to pour the water. And then you will see the tubes in the piezometers. So here is the tube in the piezometer 1. Here it is for piezometer 3 that sticks out, and piezometer 2 is inclined, which is fine. We are just going to measure the water level in that and measure the vertical distance to the where the piezometer starts to the water level, and that's going to give us the pressure head at the location P2. Then the diagram down below is that includes all the dimensions. So you can recreate this for your graphical solution and CW solution. And usually I recommend that you take the downstream water level as the datum. But in this particular case, because you are going to model this in CW, it is going to be easier if you consider datum to be the bottom of the container. Okay, so one can imagine this to be a top of bedrock or something like that. So this is what we are going to use as datum. Okay, and then you have coordinates for P1, P2, P3, and everything. So the next, yeah. So here we can see that we have maintained water levels So under this steady state seepage condition, we have the dye spreading through the soil. And as you can see, if this cutoff wasn't here, see, we have this cutoff here, the water would have gone directly underneath the dam like this. But because of the cutoff, the water is actually going under and around it. Okay. And then if we had put another dye over here, then it would have spread like this. So this gives us a very nice visual representation of how water is flowing around this hydraulic structure under steady state seepage condition. So then as this water comes out at the outlet, we used a measuring cylinder, and over a certain period of time, in this case for the first reading 61.13 seconds, 46 milliliters of water was collected here. Okay. Then we repeated it 2 more times, and these are the times and the corresponding volume of water that came out during that time. Now we have to consider the width of the container, which is perpendicular to this picture, which in this case is this width of the container, which is 7.7 centimeters. Okay. So if you imagine if the container width was twice as much, so instead of 7.7 centimeters, let's say it was 15.4 centimeters, then twice the amount of water will come out. So we have to factor that in. So in terms of finding the flow rate under the hydraulic structure, it is volume of water, which is for the first reading, it's going to be 46 cubic centimeters below, divided by the time, which is 61.13, divided by the width of the container, and that actually gives us the flow rate in cubic centimeters per second per centimeter. So you will have 3 values, and then you take average flow rate, and then you get 1 value. Okay, so that's one quantity you will need from this experiment. The other quantities we are going to need are pressure heads at point 1, P2 and P3. And I already talked about how that works, but here it is. In P1, if we have the water level here, then we just measure the distance from P2, where the point comes out of the model, to the water level. Same for P3. At this point, we measure the water level in the tube that comes out. And for P2, we have wherever the water is, we measure the vertical distance. And those numbers are here. Okay. So by assuming the bottom of the container as datum, you can calculate, let's say for HP1 or for P1, you can calculate elevation head from the diagram that we gave you. The pressure head is 4 centimeters. So using that information, you can find the total head at point P1 as its elevation head plus pressure head. Okay. So you do this to find total heads at point 1, 2, and 3. So the exit gradient is, in this case, is going to be the gradient of water when it flows from P2 to P1. Okay, so it's going to be the total head difference between P2. So this is for point 2 minus for point 1 divided by the vertical difference between point P2 and P1, which in this case is 3.6 centimeters. Okay, and that gives you the exit gradient. And then the factor of safety is critical gradient divided by exit gradient by this equation. And critical gradient is approximately about 1 for granular soils or sandy soils. So we are going to assume that to be the case, but your lab instructions go more detail into that. And the one last thing you need this for this is to come up with the hydraulic conductivity, and we are going to use it from the constant head test. Okay, and that value goes here, and you will need that for your graphical solution and CW analysis. So for graphical solution, we have given you these dimensions in your data sheets. So you are going to create on an engineering paper if you have one handy, otherwise use a plain piece of paper and select a scale, something like 1 centimeter to 4 centimeters or 5 centimeters, and convert all these dimensions that you see up here into a schematic on your engineering paper. Once again, consider the bottom to be the datum, and then for the upstream and downstream, you can find the total head on the top of the soil surface for upstream and for downstream. Okay, and then use the knowledge that you have gained in CE 180, that you try to draw 3 to 4 flow lines. So in this case, I can say that, okay, let's go underneath and divide this into maybe 1, 2, and 3 points. And let me try and draw flow lines. And we can take inspiration from what we saw in the experiment and say something like this. Okay. So this could be our flow lines. Now do your own, although I'm giving you very good sketch here. And then a little challenging part is to find our equipotential lines. So equipotential lines should be drawn such that the squares we make are approximately circles. So it is somewhat easy to do it here. Okay, so see, this is like a circle, this is almost like a circle, so you can keep on doing that and finish your equipotential lines. Okay, and you, so in this case we can find the flow rate underneath the hydraulic structure using the permeability that comes from constant head test. Delta H is the total head difference, which is essentially this value. NF is number of flow channels. So in this case, we have 1, 2, 3, and 4, or maybe the last one is 3.8. So I'm going to call this 0.8 just because, so this becomes 3.8 or something like that. And then you count the number of equipotential drops that you have, like 1, 2. So you start here with 0, then this is 1, 2, 3, 4, 5, 6, and this is going to be the last equipotential drop, which is the downstream soil surface, and that number goes here. Okay, so you have to do this by trial and error. So draw your flow net with a pencil so you can redraw it until you get a nice square flow net. Okay, and then when this is done, you need to find total heads at P1, P2, and P3 first using the flow net, and then convert those numbers using the elevation heads to pressure heads. So from this you need Q, that we are going to use this equation on the left, and then pressure heads at P1, P2, and P3. Okay? And then using P1 and P2, you also going to need exit gradient and factor of safety against exit gradient. For our numerical model CW, you basically need the soil surface, right? So you basically need, this is your origin, and then you need 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 points. So this problem is very similar to the CW lab you did. Okay? So in this particular case, our dimensions are in centimeters. So in CW, you will be better off converting all your dimensions to meters and K in meter per second. And then it will be much easier to set up your problem. And then when it's all solved, you can convert it back to centimeters for pressure heads and cubic centimeters per second per centimeter for flow rate or the flux. Okay? So in this particular case, you have our upstream is here, downstream is here, and your dam is here, right? So all of this is impermeable. We can find the total head on your upstream boundary of soil. So you need total head here, and you need total head here, okay? And then this is all soil, which the program is going to break up into a bunch of elements, right? That's how we do it. And these are your boundary conditions: total head for upstream and total head for downstream. And obviously water can't go past these boundaries. Okay? So the program will automatically assume that. So these are all impermeable boundaries. Okay? And then you will have to input a value of permeability or hydraulic conductivity and run the model. And then you will be able to see some flow lines, some equipotential lines, and so on. Okay? Then you need to find your locations of P3, P1, and P2 and find an element within that, somewhere close to it, and find a vertical gradient, and that gives you your exit gradient. Okay? And the flux should be taken from bottom of your model to the top or the bottom of the cutoff, and this is flux Q, which is in going to be in cubic meter per second per meter, and then you have to convert it to cubic centimeters per second per centimeter. Okay? And so basically you conclude by comparing the three methods, and all your values should be very close to each other with an exception of flow rate, because for hand-drawn flow net and CW, they are dependent on the value of permeability you use. So you will get 3 points there. Then you need pressure heads at point 1, 2, and 3 from all three methods, right? Exit gradient from all three methods, and then factor of safety from all three methods. And hopefully they will all match each other quite well. And then you will see that we have successfully used physical model to verify or validate the analytical methods that were based on Laplace equation. So we have provided you with data sheets with all the measurements and photographs and the schematic. So you can use this to create your report.